Hello physicists and welcome. In this session we'll be covering Momentum Section 4. Our learning objectives today are: I can identify a situation when momentum of a system is conserved, our initial and final momentums are the same, and I can identify elastic and inelastic collisions. Let's get started. Conservation of momentum. When a physicist talks about conservation, they're not talking about saving it, some quantity like energy or lights or money. When they're talking about conservation, they're saying that the amount before and after will remain the same. Remember that it's an impulse that causes a change in momentum. That our final momentum is equal to our initial momentum plus the impulse. Another way of saying that is our final momentum is equal to our initial momentum plus that change of momentum which is caused by the impulse. Momentum does not change when our impulse is equal to 0. And remember that our impulse is the product of force and time. So when there is no external force, there'll be no change in the momentum. Let's look at a couple of cases where momentum is conserved. For one object, when we have no external forces on the object. In physics, we're often talking about, let's say, spaceships deep out in space. What does that mean? No gravitational force, no frictional forces, no touching of the object, and that's a time when it's obvious there is no external force. Another time that we'll find in physics is skating across frictionless frozen ice. Neither of these conditions do we have much experience, but they end up helping us isolate when there are no external forces on an object. Another example would be an object just staying there, not moving at all. And what all these have in common is that there is no change in the speed or the direction of the object. You may have heard the expression that a body at rest remains at rest, and a body in motion remains in motion unless there are external forces acting on the object. This is case 1. Let's take a look at case 2, when there's more than one object involved, and that's collision. Collisions of two objects, actually two or more, but we're going to simplify this to the collision of two objects. Billiard balls is a pretty good example for us for a collision. What do they have in common? The forces between the two objects are very high, and the contact time is very short. The total momentum does not change if we look at both of the objects. Our initial momentum for both of the objects is equal to the final momentum of both of the objects. Hey, we've illustrated here that our initial momentum is the sum of the momentum of object 1 plus object 2 plus object 3, 4 if we have multiple objects. And our final momentum is the sum of each of the momentum after the event, after the collision. So our initial momentum is the sum of all of these individual momentums, and the final momentum is the sum of all of the individual momentums. Momentum is transferred back and forth between the objects, but it doesn't leave the system, and our system will be both objects. Okay, so let's take a little example of this. We have our, let's see, the 2 ball is being hit by the 1 ball. Momentum from 1 is transferring to 2. Let's look at this situation a little more numerically. So we know in a collision that momentum is conserved, and the momentum lost by one object is gained by the other. Our initial momentum is equal to our final momentum, and when we add each of the momentum of the individual items or objects in our system, it won't change from before to after the collision. Okay, so we have our, let's see, the 2 ball here, and we'll see that the 1 ball is sliding toward it on the right with a mass of 2 kilograms, velocity of 6 meters per second, so it has a momentum of 12 kilogram meters per second before, and it has 12 kilogram meters of momentum afterward. Notice that in the first situation, the 2 ball was standing still, so it had no momentum. So all 12 kilogram meters per second was contained in the number 1 ball. And after the collision, the number 1 ball was standing still. There was no momentum in that, and all 12 kilogram meters per second of momentum were contained in the second ball. Whatever momentum is lost by one object needs to be gained by the other. And how do we end up transferring momentum? It's with an impulse. We'll go through and allow ball 1 to hit ball 2, and we'll look at the impulse between the two of these. We'll see that the impulse is applied in opposite directions. Let's let this run. At the moment of impact, we can see that ball 1 is applying a force or an impulse to the right on ball 2. Given some values here, 240 newtons for a very short period of time, 0.005 seconds, so about 5,000ths of a second. So we have a certain impulse of 12 kilogram meters per second. That'll make ball 1 move to the right. Let's take a look at ball 1. Ball 1 was moving to the right and stopped, so we know we have to apply an impulse to the left. The force is 240 newtons for the same period of time. The impulse is the opposite direction. Notice the amount of force here and the amount of force here is exactly the same. The only difference is the direction. When a physicist says that momentum is conserved in a collision, the physicist isn't worried about the mass of the objects or the velocity of the objects. We know that the momentum lost by one object is gained by the other. Now let's take a look at this. We have a hammer moving, large mass, strikes a nail, standing still, small mass. The hammer hits the nail just as hard as the nail hits the hammer. The impulse of the hammer on the nail is the same as the nail on the hammer. The only thing that's different about it is the direction. In this case, the hammer hits the nail to the right, the nail hits the hammer to the left. This doesn't matter whether it's a baseball bat and a baseball, a truck and an insect. Forces and the time of the collision will remain the same. The only thing that's different will be the direction. We'll look at two example collisions here. The first collision is known as an elastic collision, and that's where our objects separate. We'll refer to this as an elastic collision. Again, because it's a collision, we know that the momentum lost by one object is gained by the other. Our momentum before will equal our momentum after. Okay. We'll have a baseball bat that's being swung to the right at 25 meters per second. We can see that our momentum is 30 kilogram meters per second. 25 meters per second times 1.2 kilograms. And it's going to be hitting a ball that's pitched to the left. The ball is being thrown at 50 meters per second. It has a mass of 0.15 kilograms. We see that our momentum is a negative 7.5 kilogram meters per second. Negative because the ball is moving to the left. Let's take a look at what our total momentum is. 30 kilogram meters per second minus 7.5 kilogram meters per second. Our total initial momentum is 22.5 kilogram meters per second. Okay, so batter swing, ball thrown. You see the crack of the bat, that brief instant that we have high forces. The ball and the bat separate. Afterward, we see that our bat is only moving at 10 meters per second, and the ball is moving at 70 meters per second to the right. Our total momentum for the bat, 1.2 kilograms times 10 meters per second, 12 kilogram meters per second. And our ball now has a momentum of 10.5 kilogram meters per second, 0.15 kilograms times 70 meters per second. Our final momentum, 22.5 kilogram meters per second, the same as our initial momentum. Notice that the momentum of the bat and the momentum of the ball did change. Look how much the bat changed. Went from 30 down to 12. So it lost 18 kilogram meters per second of momentum. But look how much the ball gained. It went from minus 7.5 to plus 10.8. It gained 18 kilogram meters per second. We've looked at one type of collision, the elastic collision, where the two objects separate after the collision. Now we're going to look at another type of collision referred to as an inelastic collision, where objects stick together. Because it's a collision, we still have the condition where our initial momentum equals our final momentum. To figure out our initial momentum, we'll still add up the momentum of each of the individual objects involved. But you can see here our final momentum will be the final mass times a single final velocity. Why is that? If they stick together, the final velocity of object 1 is going to be equal to the final velocity of object 2, and we'll just call that the final velocity. Hey, so we have a collision that a lot of us are familiar with. We have a large truck running down the highway at 30 meters per second, about 60 miles an hour. This truck has a mass of 2,000 kilograms. We can see its initial momentum is 60,000 kilogram meters per second. We've got a poor bug here flying along. Now it's flying to the right at 10 meters per second. Has a mass of 0.01 kilograms, about as much as 2 pennies together. So altogether it has a initial momentum of 0.1 kilogram meters per second. So our total initial momentum, we're looking at both the truck and the bug, is 60,000.1 kilogram meters per second. Let's let them run along. After our collision, our two objects are definitely stuck together. Our two initial momentums will be added into our final momentum as the truck continues down the road. Our final mass is the sum of our truck mass, 2,000 kilograms, and our bug, 0.01 kilograms, so it's 2,000.01 kilograms. Our final momentum is 60,000.1 kilograms. If we do the math, we find out that the final velocity is 29.9999 meters per second. Not much of a change in the velocity for the truck, but a big change in velocity for the bug. Hey, so now can you identify situations when momentum of a system is conserved? And can you identify elastic and inelastic collisions? So until next time, that's physics.